Let's continue on FM modulation. Last time we looked at what happens when you modulate carrier with a simple tone. And let me summarize the result from the most important result from the last time. So the most important result from last time, so that we kind of have a good starting point for today. We looked at the signal u of t, which was given as AC cosine 2 pi fct plus beta times sine of 2 pi fmt. This is an angle modulated carrier frequency fc with a single tone, 2 pi times fm. Fm is the frequency of the tone that we use for modulation. And then what we did is we did some math last time, and we kind of showed that this signal can be decomposed as AC times sum when n goes from minus infinity to plus infinity, Jn of beta times cosine of 2 pi fc plus n fm t. So this modulated sinusoidal can be decomposed as a sum of the sinusoids, which have frequencies centered around the frequency of the carrier with an integer increment of the frequency of the tone. The big part of this, which I said was a little bit, alarming from the last time, was that these boundaries went from minus infinity to plus infinity. Our only hope is that these numbers become so small that the higher order terms are negligible, right? So that the signal has a finite band. Because the way how it stands right now, this signal has an infinite band, right? Because this n goes to infinity, right? So it can go forever. Go ahead.
What's the value of n for the first one before you brought it out to the summation? No, for the one above that you got
Here?
right there.
There's no n here.
There's not like an any value, initial value of n or anything?
No, this is the modulated carrier, right? Carrier, and here is a modulated signal. This is that phi of t, right? Part of the carrier angle that depends on the message signal. Now, it turns out when this message signal is a simple tone, this modulated signal can be decomposed in a bunch of sinusoids that have this discrete spectrum. That's not very surprising to us, because we discovered that if this signal is periodic, then the big signal is periodic too. So therefore, the spectrum has to be discrete. Why so? Because periodic signals have Fourier transform, Fourier series. Fourier series means that you have integer multiples of some frequencies in the spectrum domain. The spectrum has to be discrete. All right, so that's the decomposition here, and then I have where. This is where we kind of said last time, where these Jn of beta are called Bessel functions. And we discussed a couple of ways how we can evaluate those functions. Formally, Bessel functions, just like any other function, are given in terms of a series where k goes from 0 to plus infinity, minus 1 to k, beta over 2, n plus 2k, divided by k factorial, n plus k factorial. And this expression is fine if you're a computer, but it's not very user-friendly for us, right? Because it says now, okay, you have to do a whole bunch of computations, or at least write some code that performs this summation. So, in the prior times, in times before computer, and we still use it today, engineers have developed the two aids that you have on the handout that I gave to you today. First one is the plot of Bessel functions, and you can see them how they look like. They have this oscillatory behavior. All of them are very similar except J0 of x. So let me just kind of draw a little bit. This is how J0 of x looks like. It starts from 1, and it kind of has this behavior. Here's the x, and this is the order. So this is the Bessel function of the first kind over 0th order and argument x. The Bessel function of the first kind of the first order and argument x looks like this, J1 of x, and you see all of them, here. What we're going to be evaluating in all of this is Jn of beta. So you would pick appropriate trace here, let's say J1 of 3, and then 1, 2, 3. So you kind of look it up here. This would be, if this is 1, 2, 3. This value would be J1 of 3. Okay. So that's how you read these graphs. Okay. So that's a first way how we can, yet another way how we can evaluate Bessel functions. It's not the most user-friendly. I included this so that you have an idea how these functions look like. They occur quite often in a lot of areas of physics and electrical engineering. More useful is this table, and this is pretty much the most user-friendly one too, and we're going to be using it in a lot of problems that we do. Keep it handy for your exam too, so bring in this table for the exam. Now, how does this one work? Well, you have up top, you have your Bessel functions of various orders, starting from J0 all the way to J16. And then on the first column to the left, you have the argument, right? So their argument goes from 0 to 15, right? So you have here essentially x, and then here you have Jn value. And then Jn of x is the value that you can find in this table here. So let's test your understanding. If I look at J4 of 2, what is the value? J4 of 2, no. 0.03, right? You see that? Find 2 on the far left and go all the way until you get to J4, and that's where you get 0.03, right? Okay, so that's keep this table handy. You're going to use it in all the problems that we do. But let's exercise all of this through a simple example. So, first example here. I'm going to look at a carrier, which is C of t equal to 10 cosine 2 pi fct, some carrier. And then message signal, m of t, is given as a cosine 2 pi times 10t. So this is message. And then we have FM modulation with KF equal to 50. Okay? And it says here, find the spectrum of the modulated signal. That's going to be the first one. And the second one is determine the bandwidth that contains 99% of the power. So first one is find the spectrum. And second one is find B99. That's the usually notation that I use, B for bandwidth, and 99 here tells you what percentage of the power you're capturing within that band. All right, so first thing that before we even go there, I want to kind of point out something. Let's look at power of the FM signal. Now, we have an FM signal expression, so let's look at the power. Power of FM is going to be limit when t goes to infinity, 1 over t, integral over t, x FM magnitude squared dt. That's a general definition of power. I'm just adopting it here by saying, let's assume this x here is Fn modulated signal. So when I substitute the general expression for what x Fn is, I get limit when t goes to infinity, 1 over t, integral over t, ac cosine 2 pi fct plus 2 pi kf, integral from minus infinity to t, m of tau d tau. And I have to take the magnitude of all of this, square it, and then dt. So that's an expression for power. Obviously what I have here is the Fn modulated signal. How do I know it's Fn modulated signal? Because the phase is proportional to the integral of the message signal. When I take the derivative of the phase, I get the frequency, and I take the derivative of this integral, I get my signal back. So the frequency is proportional to the message signal. So that's Fn modulated signal. In Fn modulated signal, we first integrate the message and then modulate the phase of the K. Go ahead.
Do you need to close the parenthesis on the cosine, or is all that within the, all that is within the angle of the cosine, right?
Yeah, all from here
Okay.
to here.
Okay.
And then this magnitude operates on the whole expression, like this here, right? All right, so this simplifies quite a bit. So I can say that this PFM, power of the Fn signal, is going to be limit when t goes to infinity, 1 over t, integral over t. Now this is a real signal, so this magnitude doesn't change anything. This is the square of the real signal. So I have AC squared over 2, and then 1 plus cosine of the double angle here, right? Cosine of, let me write it like this, 1 plus cosine 2 pi times 2f ct plus 2 pi times 2 kf, integral from minus infinity to t, m of tau d tau close. And then everything dt. That's the whole expression. Now you see that this falls apart and it kind of decomposes into two integrals. Let me do that here. So this becomes limit t goes to infinity, 1 over t, integral over t, ac squared over 2 dt, and then plus limit when t goes to infinity, 1 over t, integral over t, ac squared over 2 times cosine 2 pi times 2 fct plus 2 pi times 2 kf, integral from minus infinity to t, m of tau d tau. Okay? Now, what is the value of the first integral? What you need to remember, and this is, put this as a note, this is a very helpful reminder. What this does, when I say operator, limit when t goes to infinity, 1 over t, integral over t, dt, when you insert something here, what does this operator do? What does this do? If I'm taking a limit and I divide by t and integrate area under the curve, what is it that I'm doing? This is a time domain average, right? Of whatever I insert here. So this is a time domain average. So, or DC value, right? So keep this handy somewhere. This is appears all the time in communications and other areas. So if I take something, integrate it over t, divide by t, what I'm actually doing is I'm averaging over capital T. And then when I let t go to infinity, what I'm actually averaging across the entire t axis here. So what's the average of AC squared over 2? What's the average of a constant? Constant itself, right? So this is AC squared over 2. What's the average of the second one? Now bear in mind, this FC is much greater than W, where W is the bandwidth of M of t. So what is the average of this one? Another way of saying average, what is the DC component of this one? Now what does this represent? This is a modulated carrier with a frequency 2Fc. So it's way out there in the spectral domain. What is its DC component? 0, right? The average of this is 0, right? So plus 0. So the answer is AC squared over 2. Let's just stop for the moment and appreciate what the results here says. I start with a FM modulated carrier, this guy here. And regardless how the carrier is modulated, its power is AC squared over 2. Now, what is the power of unmodulated carrier? Of the magnitude AC. Same, right? AC squared over 2, magnitude squared over 2. So here, the modulation does not change the overall power, right? What happens is, as a result of the modulation, the power is distributed between side lobes and the carrier frequency, right? And we'll look into that a little bit later. But one note here is FM power of the FM signal is the same as the power of modulated carrier. This is very important because that means the FM transmitter always works at a constant power level, regardless whether the signal is modulated or not. And that's a very nice property to have. So that means your power amplifier doesn't have to be linear over a wide range of the input power levels. It's as long as you're working in a small portion of the curve, it is still amplifying fine without introducing additional distortion. Go ahead.
Can you explain why, what is it, the 2 pi 2k integration negative infinity t whatever goes to 0? That goes to 0.
This whole integral goes to 0.
Oh, the whole integral goes to 0.
Why? Because it's averaging cosine. What is the average of the cosine?
0.
0. And this is a modulated carrier. But it's when I say what is the average of a signal, what I'm really asking, in other words, is what is the DC component of this signal? And this signal is so far in the frequency domain, FC is always much larger than W, so it doesn't really have any DC component, so its average is equal to 0. Right? You can prove that more elaborately mathematically, but one of my goals is to build your intuition as well. So, big point, this is time domain averaging, and then these integrals become really easy to evaluate just by understanding what they actually represent. All right, so in this case, let's just go to our, with our problem here. In this case, what is the power of the signal? What is it? Okay, in this case, total power is what? A squared, which is, let me just put it, A squared over 2, which is going to be 10 squared over 2, which is going to be 50 of appropriate units, right? So that's the power, okay. So let's go for the spectrum, right? We see that our UFM of t is going to be 10 times cosine 2 pi fct plus 2 pi times kf. Well, let me just write it. Kf, integral from minus infinity to t, and then cosine 2 pi times 10 tau d tau. how did I write this? Well, this is my, just substituting in a general expression for the FM modulated signal, I substituted what my particular message signal. My message signal is cosine 2 pi times 10t. Right, so I'm putting it in here. And when you perform this integration, this becomes 10 cosine of 2 pi fct plus 2 pi kf is 50 divided by 2 pi times 10 times sine of 2 pi times 10t. Okay? That's my signal here. If I take it one more line, this is 10 cosine 2 pi fct plus 5 sine of 2 pi times 10t. And if you look at this one, how do we call this? No, this is beta. And this thing here is Fn. Right? That's in our, if you look at the first expression we wrote, this is the sinusoidal modulated with a simple tone, and then this is the beta modulation index, and Fm is the frequency of the tone. So based on the result from the last class, I know that this can be written as 10 sine, when n goes from minus infinity to plus infinity, Jn of 5, beta is 5, Bessel function of the nth order evaluated at 5, this thing here, times cosine 2 pi fc plus n times 10 t. So that's the decomposition of the signal into individual frequencies, individual sinusoids. Go ahead.
The F there is the one over the time period, right? Which is 2 pi 10.
Which F?
KF.
KF is the modulation constant. It's given in the problem. If you look at it over there, it's 50.
Okay, well, I'm curious on how you get 2 pi times 10.
Well, when you integrate the cosine, integral of the cosine is sine divided by whatever is here. Right? It's okay. It's okay. Just ask. All right. So we have everything we need. Now we actually need to exercise our understanding of Bessel functions and how we evaluate this. So let's do this. I'm going to tabulate them here. This is n equals 0. This is going to be J0 of 5. And you're going to help me populate this. So here I'm going to use 1, 2, 3, 4, 5, 6, and 7. And we need J0 of 5. We need J1 of 5. We're also going to need J minus 1 of 5. J2 of 5. J minus 2 of 5. J3 of 5. J4 of 5. J5 of 5. J6 of 5. J7 of 5. So let's first do this call. What is J0 of 5? Can you read it? Yeah. What is it? Minus 0.18. What is J1 of 5?
Going 3
Then J2 of 5, 0.05. J3 of 5, 0.36. J4 of 5, 0.39. J5 of 5, 0.26. J6 of 5, 0.13. And J7 of 5, 0.05. Okay? So that's these are the magnitude of all the sinusoidal components right to the kid, or the higher above the carrier frequency. Now, what do we know about minuses? You see, in this table we don't have minuses, but we derived last time an expression that says J minus n of x is equal to Jn of x if n is even, and it's equal to minus Jn of x, n is odd, right? So this one is odd, n is equal to 1. So j minus 1 of 5 is plus 0.33. This one is even, so j minus 2 is the same as 0.05. Here it's minus 0.36. Here it's the same, 0.39. Here it's minus 0.26. J minus 6 of 5 is equal to 0.13. And j minus 7 of 5 is minus 0.05. Okay? So these are the magnitudes of those sinusoidal components. Any questions so far? All right? So do you understand how I got them from the table?
Yeah.
Yeah, okay. All right, so let's draw this. The question is here, how do we draw this spectrum? And, or actually it says, well, I didn't draw it, I'm going to draw the next one, but let's, as you can see, I can keep on going, right? I can start plugging ends, and I will get ever more and more of these components. But not all of them are going to have, are going to be significant. And as a matter of fact, as n increases, you've seen from the graph that all of these functions kind of decrease. So eventually, the magnitudes are going to be very small. Now, in practical applications, I'm going to say something like this: the power of the FM signal is approximately going to be AC, well, it's going to be equal to AC squared over to sum when n goes from minus infinity to plus infinity j n squared of beta, right? Where is this coming from? Well, the magnitudes of these sinusoidals is AC times jn of beta. Therefore, you know, there will be I'm just actually using a form of a Parseval's theorem here, saying that the total power of this FM modulated signal is the sum of all the powers in each individual component here. But I can say that this is approximately AC squared over 2 sum, or I can say something like this: J0 squared of beta, that's the carrier component, plus 2 times sum when n goes from 1 to some k, Jn squared of beta. In other words, I'm going to truncate this series at some point k, and I'm going to say above k, the components give a negligible contribution to the overall signal power. And the question here is how large this k needs to be so that you capture 99% of the power. If you let k go to infinity, you capture 100%. But how large does the k need to be so that you capture 99% of the power? So to determine b is 99, we say something like this: AC squared over 2 sum J0 squared of beta plus 2 times sum when n goes from 1 to k Jn of beta squared has to be equal to AC squared over 2. This is the truncated series where we truncate up to the first k components on each side. This is the total power of the signal, and we want this truncated one to be the total power times 0.99. Right? So to capture 99% of this total power. So you can see now, the only thing that is unknown here is this k, right? So from this point, we start trying different k. What happens if k is equal to 1? What happens if k is equal to 2, 3, 4? And eventually we're gonna reach the 99% of the power. So if I generate something like this k, and here I put j0 squared of beta plus 2 times sum when n goes from 1 to k, jn squared of beta. So if I put k 1, my total power is going to be 0.24, or the summation here, 62. If I put k equal 2, I get 0.2505. If I put 3, I get 0.5167. If I put 4, I get 0.8228. If I put 5, 0.9592. We're getting there. If I put 6, I get 0.99367, 0.9993, and so on. Okay? This you can, let me give you, I know you guys use MATLAB, so let me give you a piece of code that can replicate this easily. So let's say MATLAB code here that you can type in and evaluate this. S equals 0, that's going to be this sum. K goes 6, for example. And then I can say 4, n goes minus k, 2k, s is equal, s plus Bessel j of n phi. And then n. And then when you type in s, you're going to get 0.9936. Okay. All right. So that's so the answer is what? The answer is 6. If I take the 6 components on each side, I'm going to get 99% of the power. Let me sketch this.
Can I ask a quick question?
Go ahead.
Did you have a table that you use this, or did you just run calculations?
I run calculations. What I did is, this is what I did. You write this little few lines of MATLAB, and then you substitute k equals 1,
Okay.
k equals 2, k equals 3.
So if we use this, we will have a table instead of running calculations, right?
You already have these.
Oh, you do?
They're here, right? That's right. You just need to sum them, right? Okay. But I'll give you a shortcut. You know, there is somebody actually did this work, and there is a there's a formula that I'm going to give you at the very end that kind of captures all of this. But I want you to understand where that formula is coming from. So let's draw this so that I can explain better what are we doing here. And I'm going to leave these for a little while. So here's where we're starting. We're starting with our M of f. It looks somewhat like this, right? It's a pure tone, so it has 2 delta pulses at Fm and minus Fn. Fm is going to be equal to 10, right? So that's our modulated signal. It's a pure sinusoid. Now, I can draw it like this. This is called two-sided. Or in a lot of these problems, what we are accustomed to do is to just draw one side. If you draw one-sided, then your M of f is just a single sinusoidal with a frequency Fn, right? And the magnitude of 1. Right? So what you did is you just took this folded and added together, right? So you can see the magnitude that's there. All right, so that's my M of F. I'm going to draw one-sided spectrum of my FM modulated signal. So here's FC, and I'm going to ignore these pluses and minuses. I know that they represent the phase, so all that I'm going to be concerned about is the magnitude of these sinusoidal components in the spectrum of the signal. So let me move this a little bit. So this is my carrier frequency. What is the magnitude of the component on the carrier frequency? What's the magnitude of this one?
One.
No, it's not. Huh? 0.18, right? Where did I read that?
That's a five.
Here, right here. 0.18. This is the, I'm going to say magnitude divided by 10. So this is 1, 2, right. 0.18, so here it is. Then I have 1, 2, 3, 4, 5, 6, 7, minus 1, minus 2, minus 3, minus 4, minus 6, minus 7. So these are the components that I've evaluated so far. So how about this first component? It's 0.33, so it's here. This is plus FM, plus 2 FM, plus 3 FM, and so on, minus FM, minus 2 FM, and so on, right? It's relative to the carrier frequency. So there's plus 0.33 here, there's another one, plus 0.33 here, magnitude 0.33. Then the second component is really small, is here. Then this one is 0.05, 0.05. Then the third component is 0.36, so this one goes like this. Then the fourth component is 0.39, even higher. The fifth component is 0.26, so 26, and there's one here, 0.26. So it's
There is a one.
Ah.
This one second.
did I skip? So this is minus FM, minus 2 FM, minus 3 FM, 4, 5. So the sixth is going to be 0.13. So here it is. And this one is 0.13. And then the seventh one is so small, right? 0.05. So what I'll do is just make it symmetric. 0.8. So that's the spectrum of my signal with all these components, right? Now, what was I doing in that table? I said when k is equal 1, you're cutting everything but these three components. And this is where you get that 0.2462 of the power. If you take so this is k equal 1. K equal 2 gives you the central component and two components on each side. And this gives you a power of 0.2505. Right, why? Because this one is really small contribution to power, so these two are approximately the same. But then when you take k equal 3, you're taking these three components on this side and these three components, so k equal 2, k equal 3 gives me k equal 3 gives me power 0.5167, and then k equals 6, meaning from here to here I get 0.6 9936. So in my case, to preserve 99% of the power, I have to take the carrier frequencies, 6 components to the left and 6 components to the right. The other way around, right? 'Cause I use my left hand, so that's why I messed up. So 6 components to the right and 6 components to the left. So how large is your 99 band? It's going to be 6 components times Fm, but then times 2, right? Okay? And the convenient way to write this is to take 2 times, and to realize this 6 can be written as 1 plus beta times Fm. Now, we haven't proved anything so far, but let's remember this expression here. B99 is 2 times 1 plus beta times Fm. So that's the bandwidth required to capture 99% of the power for this modulated signal. Any questions? Let me ask you. How much of the bandwidth would capture all of the power? Yeah, the entire power. This is capturing just 99%. Infinity, right? But how much of the bandwidth would capture 99.9? How many? 7. 7 components on each side, right? How do I know that? Look at the table. For 7 components, I'm capturing 0.999 something of the power. So even though you know that summation goes from minus infinity to plus infinity, it has some stuff here, but then quickly dies to the point where the contribution of the other components is negligible. Okay? All right. So one important result. So from this analysis, I want you kind of to understand this picture, how we got here, and kind of keep this expression handy, because it will start surfacing more and more in other problems, so that we generalize it. We realize that this is not an accident, so this is some relationship that we actually gave a name, and we use it to calculate the bandwidth of the FN modulated signal. All right, so that's the simplest FM modulated signal, where you take the carrier and your message signal is just a simple tone. Let's take a look at a more general case where my modulated signal is not a tone anymore, but a periodic signal, any periodic signal, right? It will include this case as a special case. But now I'm saying my message signal is not only sine or cosine, but it can be square wave, or it can be anything that is periodic. Okay? So let's take a look at that scenario.
Can I ask a quick question?
Sure.
Why is the carrier frequency magnitude 0?
It's not. I just forgot to move this. This is. Remember, I skipped one, so I tried to make it symmetrical.
Excuse me.
Go ahead.
When we want to get j minus 1 or 2, do we have to take the opposite sign of the number?
Well, depends.
Like,
You have to kind of know what you're drawing, right? A lot of here, I'm just drawing magnitude, right? So magnitude by definition is always positive. Now, if I were to draw a phase, then phase for positives was going to be 0. Phase for negatives will be pi, right? A lot of authors, since you have pure sinusoidals that can be either plus or minus, a lot of them would take and draw positives positive and then flip the negatives down. So they would say, okay, instead of minus 0.18, they would just put it down. And this is how in one graph you capture both magnitude and phase. You can do it that way. It's not wrong as long as you know what you're doing. I'm not a big fan of that, because then you lose if you're not careful, then what you're drawing is not magnitude spectrum anymore. Is something that you and I both agreed, what is it that we're representing here? You know, I'm actually taking 2 graphs, magnitude and phase, and putting that on 1, right? And it will only work for cases where the phase is either 0 or -1. If the phase is 34 degrees, there's no way for you to draw 34 degrees, so it doesn't work generally. So, but in most of what we do, really the most important thing is actually magnitude. So, you know, unless it's asked specifically, just draw everything positive. Okay. So let's extend our analysis to the cases where message signal is periodic. So angle modulation. Periodic signal. Here, our u of t, in this case, is going to be equal to AC cosine 2 pi FC plus beta and n of t. Mn of t, this n here is, it means normalized message signal. In other words, the magnitude of Mn of t is smaller or equal to 1. Now, how do we approach this problem? Where we're going to follow the same process we did the last time. I'm going to say consider this u of t can be written as the real part of AC e to the j 2 pi fct times e to the j beta n of t. How do I know that? We'll do this mind calculation. I'll multiply these two. That becomes AC e to the j 2 pi fct plus beta mn of t. Now e to the j something is cosine plus j sine. So, you know, it will have AC cosine of this plus j AC sine. And then this picks only the real part, meaning just the cosine. So this is the same thing as this. So just a notational convenience. Now I'm going to define a signal z of t. Also, Mn of t is periodic with period t, which is 1 over fn. So define z of t, which is e to the j beta mn of t. If mn of t is periodic, what can you tell me about z of t? What happens to z of t? If mn of t is periodic, what about z of t? Periodic signal too, right? As a matter of fact, the period of z of t is the same as the period of mn. When mn repeats, z repeats as well, right? So mn of t periodic. Z of t, therefore z of t periodic as well. Now, when I say the signal is periodic, what reaction does that trigger? Well, Fourier series, right? If I know the signal is periodic, I know that it has Fourier series. So z of t can be written as sum when n goes from minus infinity to plus infinity, Cn e to the j 2 pi n fm t, where the Cn coefficients are going to be calculated as 1 over t, integral over then the z of t, which is e to the j beta mn of t, and then times e to the minus j 2 pi n fm t dt. So these are the coefficients of the Fourier series expansion. I can put this into one integral, so this becomes 1 over t, integral over t, e to the j, beta mn of t minus 2 pi n fm t dt. Now this integral, you know, if I leave it like this, you cannot really evaluate it because you don't know what mn of t is. But once I know what mn of t is, then it's just another integral, right? There's nothing that prevents you from putting in whatever mn of t is, and then if you can solve it analytically, you can. If you cannot solve it analytically, you solve it numerically, but you get a single value, right? This is one number. It says for a given mn of t, it says give me beta, give me n, and I'll give you one number, right? So this is the magnitude of that particular sinusoidal component that participates in making of this signal. So once I realize that, so let's assume that we can calculate these, I can put this back into the original expression. Therefore, this u of t becomes real part of AC e to the j 2 pi SCT plus times sum when n goes from minus infinity to plus infinity Cn e to the j 2 pi n fm t. And then when you multiply everything and take the real part, this becomes AC sum when n goes from minus infinity plus infinity magnitude of Cn cosine 2 pi Fc plus n Fm t plus the angle of C. Okay? So that's the form of the u of t. Now let's stop for a moment and understand what is it that we just demonstrated here. We demonstrated that if the m of t is periodic, not a tone, but just periodic, that the spectrum is very similar to the case of a single tone. It has frequencies that are Fc plus NFM, so it has discrete spectral components that are centered at the frequency of the carrier, but with integer multiples of the fundamental frequency. And it has, the only difference is that this is now some different magnitudes. And you know, in a special case where you have a periodic signal that's a tone, these CNs become Jn of beta. In some general case, I would have to evaluate them numerically or analytically, however I can do it, using this particular integral. But the story, the moral of the story is the same. You end up with a spectrum that has discrete components that are centered at the carrier frequency and that are spaced FM hertz apart. Right? So you have, just like in that case, you have the central, one at the plus FM, plus 2 FM, plus 3 FM, and so on. Go ahead.
Would you classify this as a complex Fourier series or something from like form 2?
This is a complex Fourier series. This is a form 3.
Oh, so-
Yeah, yeah, I could, that's what I'm using to decompose it, right? So you have Cn and then Cn are calculated this way. This is a complex Fourier series, form 3. Any other? Okay,
I'm not sure about how you bring the last for a moment.
from here to here?
Yeah.
Yeah, I kind of skipped a couple of steps, so let me fill them in, right? I was rushing to get, now that you know the result, let's see how do you actually travel from here to here. I'm gonna just use this one, oh, the board. So we start with this u of t is equal to real part AC e to the j 2 pi FCT times sum when n goes from minus infinity to plus infinity Cn e to the j 2 pi n Fm t. the first thing that you realize is this Cn is a complex number. Therefore, it has a magnitude in phase, right? So I can write this as a real part, AC e to the j 2 pi Sc t sum, when n goes from minus infinity to plus infinity, magnitude of the Cn e to the j angle of Cn, right? I'm going from just a general complex number into magnitude phase expression. And then I have times e to the j 2 pi n fm t. Now let's bring everything under the same summation. So this becomes the real part of the summation when n goes from minus infinity to plus infinity, AC Cn e to the j. Now let's see what's upstairs. It's going to be 2 pi FCT plus 2 pi n FMT and plus the angle of Cn, right? All of that is on. And then I can change, both of these are linear operators, so I can swap them. Real part of the sum is the sum of the real parts, right? So this becomes now sum, n goes from minus infinity to plus infinity, AC Cn. And what's the real part of this? This is e to the jx, so there's cosine x plus j sine x. Sine x goes away, so all that's left is a cosine. So there's a cosine of 2 pi fc plus nfn t plus the angle of c. And that's what I have here. Right, the same. Okay. Couple of steps. All right, so let's take a look at what happens in a most general case. When now my m of t is not a tone, nor it is periodic. It's any general aperiodic signal. Now, how do you prove this? It actually gets it gets a little bit messy, but the similar idea as we did when we proved the Fourier transform. We're going to say, okay, I don't know how to treat the aperiodic signal, but I can make it a periodic, its periodic extension, and I decompose its extension, and then you let the period go to infinity, and you get the result. I don't want to go into that because really there's a lot of math, but the end result is quite simple. So let's just focus on end result and trying to explain what does it mean. So in general case, so this is now 3. In general case, m of t aperiodic means not periodic, any kind of signal. Also band limited, which means that f of f is identical 0 whenever f is greater than some w, right? So your frequency outside of this bandwidth w, the signal has no component. The spectrum depends now in quite complicated manner, but it can be shown that this relationship holds. Bandwidth, and this is close to 99 bandwidth, is given as 2 times 1 plus beta times W. That's the bandwidth of the FM modulated signal. So 2 times beta is the modulation index. And this W is the highest frequency in the spectrum of the signal. Okay? So how do I get the bandwidth of the FM modulated signal? Is 2 times 1 plus beta times W. Now it depends on 2 things. It depends on W, how much of the is signal wide at the baseband, but it also depends on beta, which is the modulation index. This expression is known as Carson's rule, or Carson's rule, that's the most common, in honor of the guy who derived this formula. An interesting thing is that when Carson derived this formula, the purpose why he derived this formula was to demonstrate that FM is useless, right? And the reason, the way he argued is, well, look at the bandwidth of this signal. It is 2 times W, which is the bandwidth with double sideband, large carrier or suppressed carrier. But it's never that. It's always greater, because as soon as I modulate, I'm going to exceed that bandwidth, right? I get that bandwidth only when beta is equal to 0, right? Which is, so that means FM modulated signal is always going to have a bandwidth that exceeds that of the double sideband AM. And we already talked that in some applications we regard double sideband AM as inefficient because it sends 2 sidebands, each one of them carrying the same information. So the last lecture, we demonstrated single sideband, how you can transmit using only single sideband. So this one turns out, in terms of the bandwidth, to be even less efficient than double sideband AM. It has a larger bandwidth by the factor of 1 plus beta, where beta is the depth of your modulation. How much are you modulating, right? So the Carson said, well, look at this. This is less efficient, and it is inferior to AM. Well, I mentioned that the last time. If you look at this, this expression alone, is absolutely correct. So far, in everything that I presented so far, there's nothing that works in favor of FM. Let's just look at it. The bandwidth is bigger, larger than AM. The modulation is nonlinear. You can show that if you have sum of the 2 signals, the modulated signal is not the sum of the 2 modulations. It depends in a complicated manner. So the modulation is nonlinear. Mathematically, it's complicated. There are all of these reasons that kind of discourage its use. We still have to build the case for FM. Obviously, you know that this is the most successful analog modulation there is. There are still very few analog modulated systems, but most of them that exist and that they're in use are still FM, right? So we need to build a case. And I'll remind you of that when we start talking about what is the impact of the noise in communication systems, because you will see that FM is extraordinarily robust towards noise. And that's going to be its big selling point. But so far, nothing tells me why should I even bother with FM. Just to complete this last statement here, let me give actually another expression first, an alternative expression. Also used quite often is that to say V99 is approximately 2 times 1 plus. If you remember, beta can be written as maximum frequency deviation divided by the bandwidth of the signal. So this gives you an expression W plus delta F max. So that's another version of the Carson's rule. Just pictorially too, if you were to have M of F look like this, then when you look at the FM modulated signal, the frequency, the spectrum is indeed translated to the frequency of the carrier. So this is FC minus FC. However, it's not the simple translation as I had it in AM. The spectrum here is going to look, differently than at the baseband. But what I know is that the bandwidth here is going to be 2 times 1 plus beta times W, and the bandwidth here also. 2 times 1 plus beta times done. Right? So that's, and that's really what we care about. We want to know what is the spectral footprint of this signal after modulation. Let me assign homework that accompanies this lecture. This is number 7. You have following exercises: 4-9, 4-10, 4-11, and 4-13, and assignment are problems 3-24 and 3-26. Any questions? Okay, let's take a short break and then we'll